these dots. So how do you translate that if you want to know what their average blood sugar is over a period of time, which is really important for telling if people are responding well to treatment or if they're in serious danger of going into anaphylactic shock or other health problems. So in 1994, a doctor by the name of M.M. Tai published an article in a prominent medical journal, and it talked about this. So that people used to just do this to estimate the average blood sugar. And as you can see by doing this, there's a fair amount of possible error in that. There's a fair amount of difference between how big the blocks are and how big the actual area under the curve is. And so what Tai proposed, and called it very, very humbly Tai's model, was a brilliant idea, which was you would take the same data points, and instead of drawing a bunch of rectangles, you would draw the lines between them, and then add up the area of all of these trapezoids. Now, this got published in a major medical journal, and it wasn't until someone commented on the journal and said, by the way, I don't know if you've taken calculus before, but this is called the trapezoidal rule. So many of you have seen the trapezoidal rule before. Some of you have not. But there are three things that are significant about this. The fourth thing is the trapezoidal rule actually does, in a lot of cases, work better at estimating the true average, the true area under the curve, in this case, divided by the length of the base. But it does actually a better job, this does, than this does. So that's good. The problems are three. One, Dr. M.M. Tai was embarrassed, and rightly so, by the fact that they called after themselves something which had been known for a long time, which was taught in college calculus courses. Secondly, the medical journal that approved this article, without anybody there recognizing that this is college calculus. But thirdly, and most importantly, doctors were actually using this when it was worse than this to decide on patients' treatment, which meant that people were making mistakes that they could have easily prevented, which meant that people died because someone didn't know calculus. My goal for this class is that nobody dies because you don't really know calculus. I'm going to write that out. My goal, nobody dies. Okay, I think this is a worthwhile goal. This should be a good enough goal for you, but in case you don't want to, and I stress that this actually happened, and it actually happened in 1994, which I would say is within your lifetimes, but yeah, it is. Okay, good. Just barely. But also, there's another reason, there's another course goal that is applicable here. Just about everybody here wants to be a scientist of some sort, which includes the physical sciences and the social sciences, things like medicine and psychology, and even programming. And the reason these are required for it, here's your assignment, and this is not one that you turn in, but I'm in great seriousness asking you to do this to get perspective on it. So find somebody who is currently doing a sort of job that you would like, or somebody who's in say grad school working their way towards it. So I want you to find a career role model and ask them how important calculus is to them. So I'm outsourcing this to a couple hundred different people, but what I've found in every case is that whenever somebody's in the grad school part of it or in or out practicing it, that they will say that number one, that understanding calculus ends up coming up all the time when they wouldn't have expected it, and that secondly, that they really wish they had known more calculus when they were in undergrads. They didn't have to cram on it and relearn stuff the hard way later on. So your assignment is to, don't just trust me, actually ask somebody who's a career role model how important this class is. If they tell you to blow it off, well, that's a risk I'm willing to take, but generally speaking, they're not. Okay, and of course, the sort of things that they're useful for are all over the place. Physics is a main example because calculus was invented because Newton couldn't do physics without it.